Okay, so we're going to be continuing on in chapter 10, and we're going to be covering gear trains. Okay, this is the last subject, if you would, in this particular chapter. So we are jumping ahead to 10:13, which is gear trains on page 288 in our book. So a gear train is going to be a series of mating gears to achieve large gear reductions. Okay, so for instance, if we want to go from 1800 RPMs and we want to gear it down or we want to slow it down all the way to 10 RPMs, if we would do that in one set of gears, that means that our velocity ratio is going to be 180 to 1, right? 180 to 1. And that's simply taking the 1800 dividing by 10. So we would have 180. So what that would mean, if we would do that with two gears, our first gear would be, I don't know, small, right? But then the second gear in engagement would have to be 180 times as large. So it ends up being this huge gear with this really tiny one. It probably would work. Okay, not a great design, because we now are trying to, if you remember earlier, trying to have a compact design. Okay, if we have this huge gear that we have to accommodate, now all of a sudden it's not practical, especially in the size of putting a gearbox housing around it and that kind of thing. So what we end up doing is we end up making what we call gear trains. And it means that we're going to be stacking up individual velocity ratios in order to achieve a larger train value. Okay. Now, to do this, we are simply going to break this into separate velocity ratios. And to get our train value, we are going to simply multiply what we say is velocity ratio number 1 times velocity ratio number 2 times velocity ratio number 3, and so on, however many reductions that we end up having. Okay, so this is going to be something that we're going to add to our equation sheet. So I'm going to go underneath here now, and we're going to add TV, which is our train value. We'll put that over on the left-hand side here. It's going to be equal to velocity ratio 1 times velocity ratio 2 times velocity ratio 3, and so on for however many gear reductions you would end up having. Each one of these velocity ratios is what we call a reduction. So for instance, if we have a double reduction gearbox, that means that there's two sets of velocity ratios in there, which is really a set of 4 gears. 4 gears, okay? 2 are going to be in mesh for the first reduction, and then we're going to have 2 more in mesh for the second reduction. If we have a triple reduction gearbox, that means that there's 3 sets of velocity ratios or gears that are in mesh. So that would be actually 6 gears that would be inside of our gearbox. Okay. Right. So TR is going to be equal to train value. Now, the units for a train value are going to be unitless because it's multiplying velocity ratio times velocity ratio times velocity ratio. And as we know, velocity ratios, because they're divided by the same units, top and bottom, it's unitless, right? It's just a ratio. It's just a number. Okay. All right. So this will also be unitless. So let's look at an example. Let's look at an example of what we're talking about here. So the example we're going to look at is on the bottom of page 288. And this is example 1018. Okay, that's right here. Now, as we look at this example, this is a top view directly above, if we would look straight down on what we see in our front view here. Okay, where we see the circles. So the gears, as we see them here. Now, they don't look like gears because we're not seeing the individual teeth. They are showing this so that the pitch diameters are tangent to one another. Okay, they're just not showing the teeth because otherwise it would get kind of busy. So this would be the pitch diameter of gear number 2. This would be the pitch diameter of gear number 3. And then we've got 4 and 5, 6 and 7. Now, as we look at the top view, notice that the center lines are going to be the shafts that each of these are on. Okay, so as we look at number 2, this is the only gear that is on shaft number 2 or on, yeah, I'll call it shaft number 2. Okay. Then we've got our next shaft over to the right in engagement with. So right here is the engagement point between 2, okay, and gear 3. So if we look straight down, that's where they're going to be engaged, right? Now, in front of gear 3 is gear 4. Okay, so this is gear 4 right here. If we look down here, that is going to be the pitch diameter of that one, right? It is engaged with gear number 5, okay? And then on that very same shaft is gear number 6. That's going to be on the front here, and we'll see it right there. And then gear number 7 is right there. Now, any gears that are on the same shaft are going to be going at the same RPMs, okay? So for instance, when we find out what the velocity ratio is between 2 and 3, and we find out what the RPM of number 3 is, that is going to be the same RPM as number 4, okay? Because they're keyed onto that. So they're going to be going at the same rotational speed. So when this goes around, these 2 gears are going at the same RPMs, okay? Now, with 4 engaged with 5 and 6 being on the same shaft as 5, 5 and 6 are going to have the same rotational speed and direction. Okay, I should add that too. And then lastly, 6 and 7 are going to be in engagement. And although there's no other gear on the same shaft as 7, so 7 is going to go at the RPM that it's going to be. Now let's look at direction. Okay. In this problem statement, okay, and the problem statement is here. It wants us to determine the rotational velocity of gear 7 as gear number 2 drives at 1800 RPM going counterclockwise. Okay, counterclockwise. So let's go back down here. So we know that gear 2, okay, is going counterclockwise. So that means it's going this direction, right? Counterclockwise. That's going to be W2. And we know that to be 1800 RPMs. So that's the angular velocity of gear number 2 going counterclockwise. Now, the thing about gears is whatever it's engaged with, it's going to change the direction in the opposite way, right? So if W2 is going counterclockwise, do you see how 3 has to go clockwise, right? So this is going to be W3. Now, because W3 is going clockwise, do you see how 4, it's on the same shaft, also has to go clockwise, and they will go at the same angular velocity. So W3 is equal to W4, right? And in the same direction. On the same shaft, so they're going to go in the same direction. Make sense? Now, 4 is engaged with 5. So if 4 is going in a clockwise direction, that means that 5 has to come back and go counterclockwise. So W5 is going to go counterclockwise. That would mean that the angular velocity W6 is also going to go counterclockwise. So that means that W5 is equal to W6, both in its magnitude and direction, because they're on the same shaft. And then because 6 is engaged with 7, that means that 7 then, if 6 is going in a counterclockwise direction, 7 is going to go back clockwise. Okay? All right. So we need to find out if W2 is going counterclockwise at 1800 RPM. We already know its direction, but now we have to find out how fast is that going? What is W7? What is its angular velocity in RPMs? Okay. Now, we do know some information about these gears. Okay. We know that, and this is what they're giving us. We know that gear 2 has a number of teeth of 10 and has a diametral pitch of 12. And then we know that the pitch diameter of 3 is 2.5. Okay. D3, that's pitch diameter, not diametral pitch. And then for gears 4 and 5, we know a little bit more information. And then for 6 and 7, we know a little bit more information. Okay, so using this information, we're going to be able to walk down each one of those pairs of gears and figure out how fast W7 is going, okay? Now, we also want to know, so we not only want to know how fast gear 7 is going, we also wants to know the distance between the shafts that carry gears 2 and 7. So we want to find out what is the center distance all the way from 2 to 7. So what is this distance between these? Okay. All right. So we've got a little bit of work here to do. So where are we going to start? Well, first of all, what we need to do is we need to find out what the sizes of each one of these gears are. Okay. Now, thinking ahead, our center distance is going to be the radius, if you would. Like if we want to know the center distance between these two gears, it's going to be the radius of our first gear and the radius adding to it the radius of the second gear. So that means we need to know what the pitch diameter is of each one of these gears so that we then can divide it in half to get the radius of each one and then determine what the center distance is from each one that we're using, okay? So if we look at the information that we're given, we're only given the pitch diameter of gear number 3, of gear number 5, and of gear number 6. So using what we know with the number of teeth and the diametral pitch of the others, we'll be able to calculate the pitch diameter for each one. So that's what I want to do first. I want to figure out for each one of these sets, what is the pitch diameter for each one, okay? So let's start out here with, this is example 1018, okay? And we're going to start with, I don't know if we want to call this set number 1. Set number 1, which is going to be gears 2 and 3, okay? Gears 2 and 3. So we know for gear number 1, and again, just using our information that we are given at the top of page 289, we know that the number of teeth in gear number 2 is going to be 12. And we also know that the diametral pitch is 12. And then make sure that you put your teeth per inch as the units for diametral pitch. Okay. Now for gear number 3, we don't know the number of teeth in gear number 3, but we do know that its pitch diameter, so we're going to say D3 here, is equal to 2.5 inches. So if I want to find the pitch diameter of all of my gears, notice that I need to find the pitch diameter of gear number 2 here. I know pitch diameter of 3, so that's good. But now I need to figure it out for number 2, okay? So if we go back to our equation sheets, our relationship between diametral pitch, number of teeth, and pitch diameter is this equation right here. So we can rearrange this so that we solve for our pitch diameter. So go ahead and rearrange this to solve for D2. So if we rearrange that equation, you should get D2 is equal to N2 divided by diametral pitch. So now we're going to put in 12 teeth on top here, divided by 12 teeth per inch on the bottom, right? Our teeth are going to cancel. We have inches in the denominator of the denominator, so that means it's multiplied on top. So it looks like our D2 is going to be equal to 1 inch. Okay, and I'm just going to put a little cloud around this. This is not my final answer, but now for my first set, I do know the pitch diameter for each of these, right? So I could figure out the center distance for those, but I'm going to wait till the end to do that. I want to find the pitch diameter for each one of our gears here that we don't know it for. All right, so that's set number 1. Let's look at now set number 2. Okay, and this is going to be gears 4 and 5. So these are the two that are in mesh with one another. Okay. They're the two that are in mesh with one another. So if we look back at our illustration, we just figured out the pitch diameters for 2 and 3. Now we're going to be looking at 4 and 5. 4 is in the front of 3 on the same shaft, and it's engaged with number 5 here, okay? So let's look back up at our information up on the top here. You'll notice that we know the number of teeth in number 4 is 15. We know that the pitch diameter of 5 is 3 inches, and the diametral pitch for 5 is also 10. So let's get that information. So we know that N4 is going to be 15 teeth. That's all we know about N4. We know that D5 is equal to 3 inches, and that the diametral pitch of gear number 5 is 10. And that's going to be teeth per inch, right? Now, if I want to figure out the pitch diameter for number 4 here, I have to have D4 is equal to N4, which I know, divided by the diametral pitch of gear number 4. Do I know the diametral pitch of gear number 4? I do. What is it? If it's meshed with gear number 5, they have to be the same. So they're giving us the diametral pitch for gear number 5. So that has to be the diametral pitch for gear number 4 if they are in engagement. Okay. So we know that to be 10. So we can put our 15 teeth on top divided by our 10, teeth per inch on the bottom. Teeth cancel. We have inches in the denominator of the denominator, multiply on top. So our D4 this time is going to be what? 15 divided by 10, 1.5 inches. Okay, so I'm going to put clouds around all of my diameters. And my D5 was given as 3 inches. My D4 is 1.5. Okay. I have one more set to do, set number 3, right? This is going to be gears 6 and 7. Okay. So what do we know about gears 6 and 7? We know the pitch diameter of 6. We know the diametral pitch of 8. And then we also know the number of teeth for 7. Okay. Go ahead and find the pitch diameter for number 7, D7. I want you to calculate that. Okay. D6. You should get a diameter 7 equal to 4 inches. Did you guys get that? You guys get that? Yeah. Okay. Now, since we have all of these diameters, even though they asked for the center distance second in the problem, I'm going to go ahead and calculate the center distance first, okay? Just because I've got them all, right? So I've been putting little clouds around each one of my pitch diameters. So I've got 2, 3, 4, 5, and then now we had 6 was given and we just calculated 7, okay? So what we're going to do now for that center distance, okay? So the center distance, and this is going to be from 2 to 7, okay? From gears 2 to 7, it's going to be equal to. And if we look here physically, we're going to take the diameter of 2 plus the diameter of 3, and we're going to divide that by 2 essentially, right? And that's going to be the center distance between those two. Then we're going to take the diameter of 4 plus the diameter of 5, and we're going to divide by 2 to get that center distance. And then we're going to take the diameter of 6 plus the diameter of 7, and then we're going to divide that by 2 to get that center distance. But we can do that all in one equation, okay? So what we can do is we can say that D2 plus D3 plus D4 plus D5 plus D6 plus D7, and we're going to divide that all by 2. Okay. So you would continue however many additional pairs you would have if there was more in the train. We would do that. We would continue to add. So if you add up all those numbers, so D2 was 1 inch plus 2.5 inches plus 1.5 inches plus 3 inches plus 1.5 inches plus 4 inches. Then you're going to divide that all by 2. What do we get for a center distance? Yeah. Yep, 6.75. Thank you, Tyler and Leah. 6.75 inches. Make sure you put all of your values with the units up on top. Okay, because then none of these cancel. They just add together. There's not a power here because we're adding. So we have the correct units. So our center distance, as it asked for, from 2 to 7, not 2 to 4, 2 to 7, is going to be 6.75 inches. Okay, so that's the physical distance, okay, from our first gear, the center of our first gear to the center of our last gear. That's how much space, that's how much layout, if you would, layout space that's going to take. Okay. Now, they also want to know, okay, if W2 is rotating counterclockwise at 1800 RPM, how fast is W7 going? Okay, how fast is W7 going? This is where our train value is going to come into effect, okay? So we added our equation of train value, which is the total reduction from the number 2 to the number 7, from the beginning of our trains to the end of our trains. So earlier I kind of talked about reductions, okay? In this case, we have 1 reduction, that's going to be the velocity ratio between 2 and 3. We have 2 reductions, the velocity ratio between 4 and 5. And we have 3 reductions. So this would be a triple reduction gearbox, okay? So we have 1, 2, 3 velocity ratios. So we need to find out what is the velocity ratio between 2 and 3. And we're going to multiply that by the velocity ratio between 4 and 5. And then we're going to multiply it by the velocity ratio between 6 and 7, okay? That's what this equation is for us. So our overall train value is going to be equal to velocity ratio number 1 times velocity ratio number 2 times velocity ratio number 3, or the velocity ratio of the first reduction times the velocity ratio of the second reduction times the velocity ratio of the third reduction. Now, we don't know those individual velocity ratios, but we can calculate them because we know the diameters for each one, right? So our D2 is going to be the larger, physically larger of the two that are in mesh. So remember, the smaller of the two of a set of gears that are in mesh is going to be the pinion, and the larger of the two is going to be the gear. So we're going to take the gear in each pair, and we're going to divide its pitch diameter by the pitch diameter of the pinion. Okay, so in our first one here, velocity ratio number 1 is going to be the pitch diameter of gear number 3, because that's the gear, divided by pinion number 2. All right. And then we're going to multiply that by the pitch diameter of gear number 5, which is the larger of the two, divided by the pitch diameter of gear number 4. Multiplied by the pitch diameter of gear number 7, sorry, the larger one, 7, divided by the pitch diameter of gear number 6. Okay. Now, one last convention that I like in this book is that what they do is for every velocity ratio that you calculate, they put a negative value in front of it, okay? So for instance, this first one, and this is inside the parentheses, this would be a negative. Inside the parentheses would be a negative. And then one last inside the parentheses would be a negative. And the only reason that they do that, it is not because the value is going to be less than 1. It helps us to determine if the direction that we have is going to be in the same direction as the driver, or if it's going to be in the opposite direction as the driver. So when we drew it out, we knew and we were given that W2 was going in a counterclockwise direction, right? And then when we drew it out separate reductions here down the train, we're like, oh, it looks like W7 is going to be going in the clockwise direction. So notice that these are opposite. When we have directions that are going opposite, we will end up with a negative value for our train value. If we end up with a positive value for our final train value, that means that they're going in the same direction, okay? So it just helps us with verifying directions. So what we're going to do is we're going to take negative times negative times negative. And do you see how our final answer will have a negative in front of it? So that means when there's a negative in front of it, we are going in an opposite rotational direction from what our original pinion was on gear number 2, which was counterclockwise. Our final gear, number 7, is going to be going in the opposite direction. So it's going to be going clockwise. If this would end up a positive number, so for instance, if we were only doing 2 together, that would end up a positive number. That would mean that from your first input pinion to your last output gear, they would be going in the same direction. Does that make sense to everybody? That's the only purpose of the negative. So if you're comparing your work to an example in the book, or if you're looking at the end of the chapter or the end of the book in the appendix and there's an answer, it's going to probably tell you it's negative. And that just means that nothing different than it's going the opposite of what the original input is. Does that make sense to everybody? Any questions about that? So I'm going to put those negatives in because I think it's a good verification of that direction. Okay. So now we're going to put our values in here. All right. So we're going to have a negative, and we know that our diameter number 3 was 2.5 and our diameter number 2 was 1. So this is going to be 2.5 inches over 1 inch. Units have to go in all phases of the problem. Multiplied by a negative D5, which is 3, C3, and our 4 is 1.5. Okay. And then we have a final negative D7, 4 inches, divided by D6, 1.5. Okay, so Do the math. I know I'm going to end up with a negative in front of my value, which is exactly what I'm anticipating because I already kind of drew it out that the directions were going in opposite directions. But you're going to multiply this ratio times this ratio times this ratio. And what do you get? Anyone get a number? I get a negative 13.333. Anybody else get that same value? Tyler has it. Okay, great. Aaron got it. So negative 13.333 repeating, right? Unitless, unitless, because inches cancel each time, top to bottom for each one of these. We're just multiplying the ratios together. Okay. Now, remember, this train value is all the way from, and we probably should label this 2 to 7. 2 to 7. Okay, 2 to 7. So what that means is we can set this train value 2 to 7 equal to, okay? And we would put the negative in front of here and it would be W2 divided by W7. So all the way from the beginning, all the way to the end, okay? We know that our train value right here is the 13.333. We know that W2 is 1800 RPMs. Calculate for W7. Algebra rearrangement, that's all you got to do, okay? So solve for W7. Rearrange this to solve for W7. Take that negative out. It doesn't matter. It can go, it really doesn't matter because now we're just looking for the value. So we can put the negative there. So you should get W7 is equal to W2 divided by, let's see, train value 2 to 7, right? So we know that W2 is 1800 revolutions per minute divided by, this is where we should put our negative 13.333 unitless. So we end up with RPMs. Does that make sense? I'm so sorry. W7. W7 is equal to W2 divided by. So ending up with RPMs for our angular velocity of 7, does that make sense? Are those units that we're hoping for? Yes, yes. This is unitless, remember. Okay, so what is your value for the angular velocity of 7? It's going to be a negative what? 135 RPMs. 135 RPMs? Looks like what the book has, yep. And the negative just means that it's in the opposite direction as whatever the driver was. So this is going to be clockwise as we had seen. So this is going to be your final answer. 135 going clockwise is going to be the rotational speed of W7. Now, why do we do trains? This is a great example. So for instance, we have our 1800 RPMs coming in on W2. If we would do this in one reduction, the pitch diameter of gear number 2, we calculated to be 1 inch, right? 1 inch. If we need a reduction of 13 times, right? 13 times, that would mean that we would go from a 1 inch diameter to a 13 inch, okay? In this case, our largest diameter that we have height-wise for any one of these was 4 inches. This is a much more compact, slimmer design, okay? Because we broke it into different reductions, right? So it's better on, I mean, all the way around, it's better for the space that would be needed, okay? That's why we do the trains. And we break things into different velocity ratios, different reductions. So that's going to be a problem that you're going to do that'll be very similar to one of your example problems, okay? Let me take a really quick peek back. The next example, okay, it's going to be the idler gear. So I think this is a good time to take a little bit of a break, and we'll come back and we will finish up our last subject here, which will then get us in good shape to finish up the homework. So I'm going to do a little pause on here. Okay, so we just have our very last subject here, and that is going to be idler gears, okay? Now, an idler gear has one sole purpose, and that purpose is to just change the direction from the input to the final output, okay? So let's see what an idler gear looks like in an arrangement. So if I go back underneath, and I am on page 290, and right here, section 1014, idler gears. The idler gear in this arrangement is number 3, okay? You'll notice that it meshes on both sides with the input and with the output. We don't have an overlapping here, okay? The only purpose of gear number 3 is to change the direction so that from the input to the output, it's in a direction that's desirable. So for instance, gear number 4 is going to go in the same direction as gear number 2 because of the idler in between. And let's see how this works. So what I want to do is I'm going to write this out. You don't have to write this out because this isn't an example. We'll be doing an example in just a bit. But what I do want you to see is how this idler works. So for instance, when we look between these two gears right here that are engagement, so gear number 2 and gear number 3, we would have a velocity ratio of the first reduction, okay? Then when we look at gears 3 and 4, this would be velocity ratio number 2, okay? So if I wanted to figure out what the train value was here, okay? So if I wanted to know what the train value is from 2 to 4 here, I would take velocity ratio number 1 times velocity ratio number 2, okay? And they're given the pitch diameters for each one of these. So we can say, we'll put the negative in front of each one so that we can see the directions come out here. So this would be a negative, and our gear is the 6 inches divided by the pinion pitch diameter, which would be the 2 inches. And the negative in front because we're changing direction from this one to this one. We would multiply it by the second velocity ratio, which is going to be, we'll put another negative in front of here. So between these two, the gear would be the 8 inch. So the 8 inch is going to go on top. And the 6 inch is going to go on the bottom. Okay. Now, do you notice when I multiply across, divide by the bottom, you see how this 6 inch cancels out? So I have an 8 divided by 2. Do you see that algebraically? And it's a negative times a negative, so it becomes a positive. So my train value from 2 to 4 here is going to be a positive 4. Okay, so if I wanted to, let's say I didn't need that idler. Let's say I would go directly from my 2 to my 4. It would be 8 divided by 2. So I can take this idler out of the middle and my reduction, my train value will remain exactly the same. The only thing that an idler does is change the direction because for some reason they want these to go in the same direction. Does that make sense to everybody? So that's the only reason that we add an idler. And this idler can get bigger or smaller. It can be as big as 8 inches. It can be as small as 2 inches or any number in between. That would make sense. Okay. So that's the only thing that an idler does is it changes the direction of the rotation from input to output. And we can see here when we calculate using the ratios, and you would still write them in there, but you'll notice that, yeah, that 6 inches really doesn't make a difference when we're talking velocity ratio. When we're talking center distance, that's something different. Layout. Okay, how much space this is going to take up. So you'll notice here, if we wanted to know what the center distance was between 2 and 4 was, we would take half of 2, but we would take the entire diameter of the idler. Do you see that? And then we would take half of the 8. So this would be 4 plus 6 plus 2, or I'm sorry, plus 1. That would be the center distance. So the idler, your center distance will always be across the full diameter, but it cancels out when we look at the train value. Okay, so it's kind of interesting. So we're going to do an example that has an idler in it, okay? And that is going to be, instead of an example out of the book, we're going to use problem 1053, okay? We're going to do problem 1053. Now, 1053, it's using the illustration directly above here, okay? So as we look, you're going to notice that in this train, we have 8 gears. The first 2 gears, 2 and 3, are in engagement, okay? The next 2 gears are 4 and 5. And then 5 is also engaged with 6. So number 5 is our idler because it's engaged on both sides. Do you see that? Then 7 and 8 are going to be the last 2 that are engagement. Okay. So it's giving us some information about each one of those gears, whether it's number of teeth, diametral pitch, and pitch diameter. So we'll look at that in just a bit. But it says here that we want to determine the velocity of gear 8. So what is the rotational speed of gear 8 as gear number 2 rotates counterclockwise at 1200 RPMs? Okay. And then we also want to determine what the center distance is between the start and the finish shafts, centers of the shafts. Okay. So very similar to the last problem that we did. But again, I want to show you how an idler works because it's going to be similar to one of the homework problems that you're assigned. Okay. So what we're going to do is we're going to start here and we are going to identify our velocity ratio. So our first velocity ratio is going to be between 2 and 3. Okay. So this is going to be velocity ratio 1, if you would. Our second velocity ratio is going to be between 4 and 5. So this is going to be VR2. Our third velocity ratio is going to be between 5 and 6, VR3. And our last velocity ratio is going to be between 7 and 8. So that's going to be velocity ratio number 4. Okay. Now, to calculate those velocity ratios, we have to have similar items for each one. And as you can imagine, like our last example problem, they kind of mixed up the information here a little bit. So they're giving us for number 2, the number of teeth and the diametral pitch. And for number 3, they're giving us our pitch diameter. So again, because we are looking ahead and we know that we also need to determine the center distance between 2 and 8, it's a good idea to just do the pitch diameters for everything. So we have pitch diameter for number 3, but we'll have to calculate it for number 2. Then we're given pitch diameter for number 4. We'll have to calculate it for number 5. And then you'll notice we have it for number 6. We have it for number 7. And then for number 8, we'll have to calculate it. It says in the problem, N7 is equal to 1.5 inches. That should be D7. So the pitch diameter 7 is 1.5 inches because the units are in inches. So that's going to be a pitch diameter. So let's go ahead and find out any of the unknown pitch diameters that we need. So we'll look at this in sets again. So this is going to be problem 1053. Okay. And we're going to look at our first velocity ratio, our first set. So this is going to be velocity ratio number 1 is going to be gears 2 and 3. Okay, gears 2 and 3. We know that the diameter of gear number 3, already gave it to us in our problem, is going to be 8 inches. Okay. And we know that the number of teeth on gear number 2 is 16 teeth. And that the diametral pitch of that gear is 16. Okay. So we need to calculate. I'm going to put my little cloud around D3 because we have that one already, but we need to calculate the pitch diameter of gear number 2. So go ahead and find the pitch diameter. Use your equation sheet and we'll compare in just a bit. So I'll give you a chance to write down. You want to find out D2 is equal to, how do you calculate the pitch diameter of gear number 2? Did you get a pitch diameter for number 2 of 1? Okay. Then we want to go to our next set. Our velocity ratio number 2, we look back over here, is going to be gear 4 and gear 5. Okay, gear 4 and gear 5. Oops. I have here, there we go. Okay, so let's see what we know for that one. So it looks like we know the diameter, pitch diameter number 4, is going to be 1.5 inches. Okay, so that's one that we know, which is good. And then the number of teeth in 5 is 50 teeth. And the diametral pitch is 10. Okay, so go ahead and find T5. You should get 5 inches for the pitch diameter of 5. Everybody get that? We have another velocity ratio, number 3. That is going to be between 5 and 6. Okay, remember we have another velocity ratio. 5 is going to be included in. So this is going to be gears 5 and 6. So we look at the information that we're given. We already calculated the diameter of 5 is equal to 5 inches. We did that from the step above. And the pitch diameter for number 6 is given to us, and that's going to be 5.5 inches. So this one we don't have to calculate anything for. And then we have one last velocity ratio. Okay. So the velocity ratio, number 4, is going to be gears 7 and 8. So given to us here, we have the pitch diameter of number 7 is our 1.5 inches. And then we have the number of teeth of 8 is 56. And the diametral pitch of number 8 is 8. Remember, teeth per inch are the units there. So we've got the pitch diameter for number 7. We need to find the pitch diameter for number 8. So you should get 7 inches. Okay. Everybody get that? Okay. So now we'll do our center distance first, since we have all of these pitch diameters, okay? And we're going to look at our illustration. So remember, we have that idler number 5 in there, okay? So as we look across here from gear number 2 to the shaft where gear number 3 and number 4 are mounted, the center distance here is going to be the radius of gear number 2 and the radius of gear number 3. Do you see that? Okay. So that means that for our center distance, And this is going to be from 2 to 8. We're going to take the diameter number 2 and we're going to divide that by 2. We're going to do these separately because it's not going to be all of them divided by 2 because we've got that idler. Okay, so that'll be the radius number 2 plus diameter 3 divided by 2, which is going to be the radius of gear number 3. Plus. Okay. Now, from the center of gear number 4 to the center of gear number 5, it's going to be the radius of 4 and the radius of 5, right? So we're going to take D4 divided by 2 plus D5 divided by 2. Okay. Now we're going to go from the center of where gear number 5 is on, and we're going to go to the center of our next shaft, which is going to be the radius of number 5 plus the radius of number 6. So it's going to be D5 divided by 2 plus D6 divided by 2. So do you see how this is actually the diameter of 5? Do you see how that's the full diameter? Because we're taking the radius on one side plus the radius on the other. Okay. Don't forget that. That's why you don't want to do all of them added together divided by 2 because you would be forgetting the extra radius on diameter number 5. Does that make sense to everybody? Because either we're going straight across. Okay. And then now that we're at the center line of where 7 engages with 8, now it's going to be the radius of 7 plus the radius of 8. Okay. So plus D7 over 2 plus D8 over 2. That'll be the full center distance. Okay. Now, if you wanted to write this where this would be just D5 between these two, that's totally fine. But I wanted to show you how that idler, we have to add in for center distance, it's full diameter, not just half one time. Okay. You have to do both halves each time for each. So now you can put your numbers in. So go back and put in each. I'll put mine in here. Just got to go back. Let me know when you get a number for the overall center distance from gear number 2 to gear number 8. Tyler got 17. Let's see. 0.25. Did anybody else get that same value? Aaron did, Liam did. Awesome. Okay. So then we can put a box around that. I don't have the final answer in front of me right now. So 17.25. Awesome. Now that's center distance. The other part of this problem is we want to know what is the rotational speed of number 8 and its direction. Okay. So now to get that full train value, we're going to take the velocity ratio of number 1 times the velocity ratio number 2 times velocity ratio number 3 times velocity ratio number 4. Okay. So our train value from 2 to 8 is going to be, now put that negative in the front because then this will confirm or give us the direction of the output number 8. So it's going to be velocity ratio number 1, negative, times negative velocity ratio number 2, times negative velocity ratio number 3, times negative velocity ratio number 4. You only need to put these negatives in front when you're doing the train value. You don't need to do it if you're doing it of individual ones. Does that make sense to everybody? Okay, it's just when we're doing an overall train value. And all that the negative does is give us the direction, whether it's going to be in the same direction or not. And we can see that when we multiply negative times negative, positive, positive times negative, negative, but then it's going to end up positive as its final answer. Okay, that's all that the negative does. That's it. So we're going to put in our values now for our train values. So we know that we can figure out an individual velocity ratio by using the diameters, right? And again, on top is going to be your gear and your pinion of the two that are in engagement. So the smaller of the two is going to be the pinion. The larger of the two is going to be the gear. So when we look at our first one here, that is going to be the two gears. So this is going to be negative D3 over D2 times negative D5 over D4 times negative D6 over D5 times negative D8 over D7. Again, the larger of the two will always go on top. We can see here that our D5 would cancel out, right? You could either cancel it out and leave it, or you can put the numbers in and they will naturally cancel out. But I'm gonna leave them in there. So my numbers are going to be negative. So D3 was 8 inches. D1 was 1 inch. Inches are going to cancel. The next one, D5 is 5 inches. And D4 was 1.5 inches. Then I've got D6, 5.5 inches, and I've got 5 inches for number 5. So here you can see they're going to cancel out. Again, the only purpose of that idler, it will not change the train value at all. It will only change the direction. And then our last one is going to be 7 inches on top and 1.5 inches on the bottom. Inches cancel for each one of these, right? So our velocity ratio, we already know is going to be a positive value. Tell me what you get for the velocity ratio. Tyler got 136.89. Remember, this is unitless. And the positive just means same direction as driver, which is our number 2. Anybody else get 136.89? Aaron did. Okay, I've got shakes of the head in the room. Awesome. Now, this is not a final answer. This is just our velocity ratio from the very beginning to the very end. Okay, so we still need to figure out what W8 is. Okay, W8. So we know that our train value from 2 to 8 is going to compare W2, which is going to be our, was that 1200 RPMs. And then this is going to be our W8. Okay. So we need to find W8. So rearranging this equation, we can say W8 is going to be equal to W2 divided by the train value from 2 to 8, the train value that we just calculated, right? Okay. So now we can just put in our values. 1200 RPMs for W2. Our train value 2 to 8 was a positive on the previous page, 136.89. Okay, if there was a negative, we would put the negative in front, but it's positive. Nothing to cancel, and our units are going to be RPM 4, W8. What do we get? 8.77 RPM. Anybody else get that same value? Aaron did? Okay, fantastic. So this is our final answer, and we need to put in the direction. So since our W2 was counterclockwise, that means it's going in the same direction as that original driver, so it would also be counterclockwise. All right. So that takes us to the end of our chapter, okay? And you would be ready then to continue or to finish up or work on all of the homework problems that you have. So what I'm going to do is I'm going to stop this video here, and we are going to then look at the homework problems, and I'll record that on a separate video. So I'm going to stop.